All right, so in this video, we're going to take a look at some example questions from ALEKS in the chemical reactions, chemical equations, and calculations section. So the first couple questions here look at reduction and oxidation, and there are several, at least a couple different mnemonics you can use to help you remember what oxidation and reduction are. One thing to keep in mind is that you can't have one without the other. So if something is undergoing reduction, something else has to undergo oxidation. We can look at what's known as the oxidation numbers. To determine whether something is undergoing reduction or oxidation. So if something is undergoing reduction, that would mean a decrease in the oxidation number. And if something is undergoing oxidation, then that's the opposite. That would be an increase in the oxidation number. So what is the oxidation number? How can we identify what it is? So in this first example, we're looking specifically at the hydrogen, the H, and seeing whether or not it is undergoing oxidation or reduction. So a couple of things to keep in mind. We don't know what these oxidation numbers are on either side of the equation. We need to determine them. One of the rules is that when you have an element on its own, its oxidation number is 0. So in the case of H2, because that's the way that hydrogen exists normally, its oxidation number is going to be 0. That's the elemental form of hydrogen. And in the H2O, if we don't know what hydrogen is, we can look at the oxidation number for oxygen to help us. Oxygen in combination or in a compound will always have an oxidation number of -2, which means now both hydrogens have to equal +2 to cancel that -2 out, which means that one hydrogen then has to equal +1. So in this reaction, hydrogen goes from an oxidation number of +1 to an oxidation number of 0. So it is undergoing, so H undergoes reduction because that is a decrease in the oxidation number. Another way we can look at this is that we look on the left side, hydrogen is here combined with oxygen. On the right side, it has lost that oxygen. So oxidation, reduction would mean where we take away oxygen from something. And that's exactly what's happening with the hydrogen in this case. So it is undergoing reduction, both in terms of the oxidation number, but also in terms of losing oxygen. So that one's a little bit more straightforward to see. In the second example, we have NH3 combining with H2SO4. I am omitting the coefficients just for simplicity's purposes, and I'm also omitting the state symbols. We're just focusing now on the elements. So we're looking here at the nitrogen on both sides of the equation. So we're looking to see as it goes from the reactant to the product side, how is the oxidation number changing? So in the case of nitrogen, if we don't know what it is, we can look at the hydrogen. Hydrogen typically in combination or in a compound will have an oxidation number of +1, and we have 3 hydrogens. So that gives a total of +3, which means the nitrogen, in order to cancel that out, needs to be -3, right? Because overall this NH3 is neutral. And then on the right side, we can see here that the nitrogen is in combination with hydrogen in terms of the NH4. Now remember, that's the ammonium ion, NH4 plus. And we just said that hydrogen is normally +1, and we have 4 H's, so that gives a total of +4. And now when we add together whatever the oxidation number of the nitrogen is, we have to equal now that +1 charge for the overall charge for this ammonium ion. So the nitrogen here also has to be -3, because when we add -3 to the +4, we end up with the charge on the ammonium ion, NH4. So nothing, the nitrogen's oxidation number isn't changing, so it's neither oxidized nor reduced. in this reaction. Let's jump down. We can do the last one there. We're looking at potassium iodide combining with copper 2 chloride to give copper iodide plus iodine plus potassium chloride. And we're looking at the copper specifically. So this thing. Okay, and again, the coefficients don't affect, the coefficients are only there to balance the equation. They don't affect the oxidation numbers. So if I don't know what the copper is, I can look at the chlorine, typically -1. And I have 2 of them, so that's -2. In order for this entire thing to be neutral, the copper then has to be +2. In the case of the copper iodide, iodine, just like chlorine, is in group 7, so it usually has a -1 charge. So the copper, in order to cancel that out, has to be +1. So the copper's oxidation number goes from +2 to +1. That's a reduction in the oxidation number. So the copper is undergoing reduction. All right, let's take a look at identifying the different types of reactions. So we have the first one here. We have H2O2 turning into H2O and O2. All right, so again, I'm omitting the coefficients and the state symbols just for simplicity's sake. We have one type of reactant breaking down to multiple, so 2 or more products. That's the definition of a decomposition or breaking down reaction. In the second one, we have AgNO3 plus KBr to give KNO3 and AgBr. So what you're seeing here is the silver and the potassium are actually swapping places with each other. So the potassium then combines with the nitrate to make potassium nitrate, and the silver combines with the bromide to make silver bromide. So this would be an example of a double replacement reactions where the 2 metals in this case are swapping places. Sometimes double replacement reactions are also called, or also known as, metathesis. And I think that's one of the options that you have. And the third one, we have zinc and FeSO4 to produce zinc sulfate and Fe. So here what's happening, we have the zinc and the iron. The zinc comes in, kicks out the iron, so the iron now is by itself, and the zinc takes the place of the iron to give the zinc sulfate. This would be an example of what's called a substitution or a single replacement reaction. In reactions like these, you typically have a metal replacing another metal from a compound to make a new compound, and you have that metal displaced. All right, so it's next question is looking at writing a chemical equation from a description. So here, this is the whole point of chemical equations, is that they're used to represent chemical changes in a very concise way without losing any of the information. So it says solid potassium chloride. So potassium chloride, we need to know the chemical formula for that, and we learned all about that in the last week. So potassium chloride, we need to know the ions, that would be KCl, and it's a solid, so we need S as our state symbol. Is produced, so this is telling us that this is produced, so this is the product now, so this is go on the right side, by the reaction of chlorine gas and solid potassium. So chlorine gas, Cl2, chlorine exists as a diatomic molecule, and solid potassium. So those two react together. Potassium is K and it's solid. And now we're making that product. So on the right side of the equation, so that goes down, KCl go on the right side, and that's our solid. All right, that's our basic equation. We need to balance this. right? So we have 2 chlorines on the left. We need to put a 2 in front of the KCl. So we have our 2 chlorines. We've now made 2 potassiums. We need a 2 in front of the potassium. And that's our balanced equation. All right, next one looks at predicting the product of a combustion reaction. Okay, and a combustion is another type or classification of a reaction. And typically what we have in a complete combustion is the reaction with oxygen. And then the products that we get are usually, for complete combustion, or to produce, we get CO2, carbon dioxide, and we get water vapor as our products, right? So all we need to do here is to go ahead and write out, we have CH3, CH2OH, that's a liquid, and then the combustion reacting with oxygen, and then our products here would be CO2, and then we also get H2O. And then you would need to go ahead and need to insert your coefficients to balance this equation, right? You get lots of practice in this chapter with balancing equations. You'll apply it in this particular problem. All right, and then the next question, again, identifying reaction types. So we have precipitation, combustion, acid base. Let's take a look at the first one. So we have HCl, that's hydrochloric acid, AQ, reacting with NaOH, that's sodium hydroxide, produce NaCl and H2O. So typically here, what we're seeing is something that we saw before. The hydrogen and the sodium are swapping places with each other. So this would be a double replacement. But typically when you get something like an ionic compound and water as your products, that tells us that it's also an acid-base reaction, right? So HCl is actually hydrochloric acid, sodium hydroxide is a base. So we have a double replacement. And then this is also acid-base. Usually when you see hydroxide in a formula, that's your clue that it's a base. And it would be an acid base. All right, we have the next one, we have Mg. And again, I'm going to omit the coefficients, solid reacting with sulfur, solid to make magnesium sulfide. And in this case, we have multiple reactants. So more than one reactant combining to produce one product. So that tells us then this is a combination. Combination reactions are also called synthesis reactions, right? 2 terms that are used interchangeably. And then the other 2 we've seen before as well. All right, let's take a look at some calculation type problems now. So it says a chemist weighs out 4 grams of iron. Iron is Fe. Calculate, we need the number of moles of iron. All right, and this is now getting back into the calculation side of things. We're going from grams to moles. Okay, that's what we're trying to do in this problem. What relates grams to moles? Well, we're going to use here the molar mass, right? The molar mass is the relationship that relates grams to moles. And for the molar mass of elements, we can look them up from the periodic table. So for iron, we look it up, we see that 1 mole of iron, we just read it from periodic table, 55.85 grams. Fe in every 1 mole of Fe, right? So it's the atomic mass that we look up. We just change the unit to grams, and that's 1 mole. So if we have our 41.4 grams of Fe, right, this is my equality. I can turn it into a conversion factor, stick it in here. If I want to end up with moles as my unit, I'm going to put the moles on top. So 1 mole of Fe, and then my grams underneath, 55.85. And I do it that way because I want the grams to go away. We cancel, and I have moles of unit left as my, I'm sorry, moles of iron left as my only unit, right? So that's grams to moles, or you can go in the other direction, moles back to grams by using the molar mass. You need to calculate this and round it to the correct number of sig figs. All right, next problem. Chemical formula for lithium fluoride is LiF. And she finds that they produce 97.7 grams of lithium fluoride is produced. Calculate the number of moles. So again, here we're going from grams to moles. We need moles of LiF, again, grams of something to moles of something. We're going to use the molar mass, in this case of lithium fluoride. So we can calculate the mass of the molar mass of lithium fluoride by using, again, the periodic table. We have one lithium, the mass of 1 mole of lithium plus 1 fluorine. All right, so fluorine is 19.00. And then lithium, what is lithium? 6.94. All right, so that's going to give us 25.94 grams of lithium fluoride for every 1 mole. Lithium fluoride, that's your molar mass. We can start with the mass that is produced in this particular process, 97.7 grams of LiF. Take our molar mass as our conversion factor. Moles go on top because I want to end up with moles as my unit. 25.94 grams of LiF on the bottom. They go away and I get moles left here as my unit. I'm going to use your calculator, round it to the correct number of sig figs. All right, next one says the chemical formula for talc is given, which is found in talcum powder. So we have Mg3Si2O5, all of that 2 times, and then we have OH 2. All right, and they find that there are 22.6 moles of magnesium in this sample, and we need to figure out the number of moles of Si of silicon in that sample. All right, so one thing, this may sound like a problem or look like a problem that's fairly challenging, but it's actually really, really simple if you understand how to read chemical formulas, right? And what we did last week was putting together chemical formulas. Now we're using that information to do some calculations and to make some relationships. So these subscripts that we see in a chemical formula, whether it's something simple or whether it's a little bit more complicated like this, those subscripts give a mole-to-mole ratio. So if we know, if you have a sample of this and we know how many moles of one thing we have, we can use that ratio to calculate the moles of any other thing in that substance. So if I look at the 2 things involved, I need magnesium and silicon, right? So if I look at the subscripts, well, I have 3 moles of magnesium in every one of this entire thing. And for every one of this entire thing, I have 2 silicons, but remember now, that is in parentheses twice. So 2 times 2 would actually give me 4 moles of silicon in this entire thing. So what this is saying is that I have 3 moles of Mg for every 4 moles of Si, right? I'm just looking at the subscripts from this substance. That's my ratio. And it's always going to be that ratio as long as it's this substance. So it's saying now, if in the substance you actually have 22.6 moles in the sample, whatever the sample size is, moles of Mg, right? I can use now this ratio. I can stick it in here just like I do any other conversion factor. If I want to end up with moles of silicon, I'm going to put my 4 moles silicon on top, my 3 moles of Mg goes on the bottom because I want the moles of Mg to cancel, and I just need to then multiply and divide out. And I'll get my moles of Si. You want to round it to the correct number of significant figures. All right, and we have the next problem. It says to balance the chemical equation using the smallest possible whole number stoichiometric coefficients. All right, those are just the numbers you put in front of the formulas to balance. And balancing equations really boils down to trial and error. However, when you watch the videos, you'll see that there are some strategies you can use to make the balancing process go by a little bit quicker. So please make sure that you take a look at those videos. All right, the last couple problems here look at stoichiometry. All right, so stoichiometry is a big part of chemical equations, chemical reactions, and this is where we apply some of the math to determine, in conjunction with the balanced chemical equation, to determine how much of the quantities of reactant or products we're going to be needing or that we're going to produce in a particular reaction, right? That's all that stoichiometry, the big fancy word, just means the amounts involved in that chemical equation or chemical reaction. So let's take a look at the first one. Well, let's take a look at the second one, actually. So it says ammonium phosphate is an important ingredient in many solid fertilizers. It can be made by reacting now aqueous phosphoric acid. So if I take the H3PO4 and I react it with ammonia, so ammonia by now we'll know as NH3, to make NH3PO4 or NH4 ammonium phosphate. All right, so that's our equation. You weren't given that equation explicitly, but you were told that that's how you make ammonium phosphate, by reacting phosphoric acid with ammonia. All right, so we're going to use that equation. However, before you use it, you want to make sure that it is balanced. Okay, so it needs to be balanced. So you want to go through and you're going to use your coefficients to balance this particular equation. All right, so we're going to balance this. And again, just by inspection, on the right side, we can see that we have 3 times 1. We have 3 nitrogens. We have 1 nitrogen on the left. So if I stick a 3 in front of this, that gives me now 3 nitrogens. How many hydrogens do I have on the right side? I have 4 times 3 is 12. Hydrogens on the left, I have 3 times 3 is 9, plus this 3 is 12. Phosphoruses on the right side, I have 1 phosphorus here. On the left side, I have 1 phosphorus. On the left side, I have 4 oxygens, and then on the right side, I have 4 oxygens, right? So this is my balanced equation. And your equation needs to be balanced before you do any sort of stoichiometric calculation. So it says calculate the moles of phosphoric acid needed. All right, so that's what we need to calculate, the moles of this thing, to produce 2.14 moles, 2.1 moles of ammonium phosphate. Okay, so 2.1 moles of this is what we need. We need to figure out the number of moles of H3PO4 needed. Okay, so looking at my balanced equation, I can see that my mole-to-mole ratio here. So we're going to use that mole-to-mole ratio. And that's just reading the coefficient. So it's just 1 mole of H3PO4 for every 1 mole of the ammonium phosphate. Okay, so I know how much of this I need to make, so I can start with that. So 2.1 moles of NH4 3PO4. And then I can take my mole to mole ratio, insert it as a conversion factor. If I want to end up with the moles of H3PO4, that goes on top. So 1 mole of H3PO4 for every 1 mole of NH4 3PO4. So obviously with the 1-to-1 mole ratio, we get the same number, right? So 2.1 moles of phosphoric acid would be needed. This particular problem. So you want to ensure that you have an equation written and it needs to be balanced. The numbers that we use to balance that equation, those are your mole to mole ratios. And that is the key thing in any stoichiometric calculation. You need those coefficients. They give you that mole to mole ratio and they relate one thing with any other thing in that reaction. All right, and then the last one we'll take a look at here is very similar in terms of the stoichiometry involved. Where are we? Okay. So it says ammonium perchlorate is a solid rocket fuel that's used in the space shuttle, using the space launch of the Artemis rocket. So it reacts with itself. All right, so we have NH4 ClO4, and if it's reacting with itself, that means we're going to have 2 of it to produce. So to produce now our arrow, we have nitrogen gas, we have chlorine gas, Cl2, we have oxygen gas, and then we also have H2O. And we get a bunch of energy, which is the whole point of this. All right, so we need to make sure that this is balanced. So let's see, we have 2 nitrogens, they look good. 2 times 4, 8 H's. So we need maybe 4 in front of the H2O. Let's see. Does that make sense? Yeah, so 4 times 2, 8 H's. We have 2 chlorines over here. And 2 times 4, 8 oxygens. We have 4 over here. We need another 4. So 2 times 2 is 4. Plus that 4 is H. All right, so we have our balanced equation. Then we can go ahead and do any sort of stoichiometric calculation. So it says what mass of chlorine gas is produced. So chlorine is this thing. That's what we want to relate by the reaction of 3.1 grams of ammonium perchlorate. That. So these are the 2 things we're trying to relate. All right. And we're told that we're starting with 3.1 grams of NH4ClO4. We want to determine the mass in grams of Cl2 that's produced. All right, so we want to go from grams of a reactant to grams of a product. And the only way to do that, the only way to relate any 2 things in this equation is to go through moles, right? So we need the mole to mole ratio of those 2 things. The NH4 ClO4 to the Cl2. And that is from the equation, a 2-to-1 ratio. But we're not given moles to start with, we're given grams. So we first of all need to convert the grams into moles of NH4 ClO4. Then we can use our mole to mole ratio to convert moles of the ammonium perchlorate to the moles of chlorine. We can then determine the moles. As a result of that, we'll get the moles of Cl2. Once we get to moles of Cl2, then we can convert that to the grams of Cl2. How do we get from grams of something to moles of that thing? We're going to use the molar mass of NH4 ClO4, right? So we've done a couple of these already. So we just add all of these together, the individual molar masses. That'll give you the molar mass of this entire thing. We just end up dividing. So let's say we have now our 3.1 grams of NH4 ClO4. My molar mass, okay, we're going to determine that every 1 mole of ammonium perchlorate. We add up the 4 oxygens, the chlorine, the 4 H's, and the 1 nitrogen, and we get our molar mass. All right, so that gives 117.49 grams. So the grams cancel out. We are at moles of ammonium perchlorate. We can then use our mole to mole ratio from the balanced equation. All right, so we have now the moles of ammonium perchlorate needs to go on the bottom because I want to cancel that out. So 2 moles of NH4, ClO4, I get that from the equation, produces 1 mole of Cl2, right? That's my mole to mole ratio that I'm inserting here. The moles of ammonium perchlorate goes away. I'm at moles of Cl2. Now I can use my molar mass of Cl2 to convert moles to grams. Okay, so I can look that up on my periodic table. The molar mass of chlorine gas. All right, so we have 35.45 times 2. That'll give 70, what is that, 70.91 grams of Cl2, and that's for every mole of Cl2. Moles goes away. I end up now with the only unit left, which is grams of Cl2. That's my final product. And I need to use my calculator and evaluate this entire thing. All right, so this is as complicated as you'll see in a stoichiometric calculation, starting with grams and converting it to grams of something else in that equation. You can't do this unless you have a balanced equation, properly balanced, so that you can use those coefficients as mole to mole ratios.